Hi, everybody. Good afternoon. I hope you had a great lunch. Kind of continuing on the theme that we heard in the early keynote from my colleague Anthony, and if you caught Dean's talk about OSS and open science, we're going to go into a little bit more detail today on one of the projects we're working on, something called the OpenAD framework. The goal of OpenAD framework is very simple. It's to solve some of the problems that we saw in terms of the exchange of data, the reusability, a lot of the neat and fun things we know about open source, and apply it to science overall. So let's get started. So accelerated discovery is an interesting term, two interesting words together, but it means something very specific within the context of the work we do at IBM Research. Every year we have something called the Global Technology Outlook. We put together a very fun, glossy paper for the market and our internal teams. And a few years ago, we did one on the idea of accelerating materials discovery. So what does this mean? Materials discovery can be anything from things like replacements for PFAS or forever plastics or materials. It could be better photoresistant materials so we can make higher fidelity integrated circuits and gates. It can be the idea of carbon capture tools and facilities and carbon sequestration scenarios. All really interesting fundamental applications of how we're working through this idea of improving our life overall. This also happens to apply to the identification of molecules for use in small molecule drugs, the materials that you might use to improve the delivery of drugs, things like higher temperature vaccines for COVID, for example, lots of other options in that category. And that's how it worked. So we did a paper talking about how we could apply a couple fundamentals of AI, quantum computing, a few other components to those areas with the objective of not just offering these technologies, because we've been doing this for a long time. Some of the people on that list from the paper built Summit, one of the early supercomputers. We've got a lot of experience with high-performance computing and a few other pieces, but we wanted to take some of this technology and drive more availability, more accessibility to the general population overall, because we really think the way to go, just like open source, with open science, is to get as many people involved as possible so we can start to share in execution and targets. So we looked at 4 fundamental areas. We looked at the idea of what we call deep search, or the analysis of the corpus and body of information available. Most molecules that you want to use for materials or drugs are actually packed into papers that are shoved into repositories like arXiv, and it's really hard to tell who owns what. The other half of them are put into patents and patent databases as part of that story, and you want to really understand A, what's available, B, what you can use, and C, how does it relate to the problem you're interested in? So how do I relate properties to a specific molecule in terms of how that works? And that's what this DS4SD is. ST4SD is a simulations technology, which is fundamentally centered around the idea that when you're screening whether a molecule works or not, you have to simulate it, either classically, Newtonian simulation, quantum mechanically, or otherwise, so you have a good sense of whether it will actually work in a situation. And that includes things that you would probably not initially think of, like making sure that it's stable in 960-degree Kelvin water, meaning U, and other aspects of how things work in this category. And that's really a powerful way to do that. We also built something called GT4SD, which is eminently relevant. Now 5 years in, GT4SD is a good example of early applications of generative models and the ability to essentially drive to a property-driven outcome for this. So what happens here is you input a set of properties. I would like something that is conductive or non-conductive and stable at this temperature target and a variety of other categories. And what it will do is cycle through and, just like an LLM, generate the next token in terms of the overall molecular structure necessary to define a candidate molecule as part of that story. Now, this is where things get interesting. A lot of people will take a library like GT4SD and put in a property like toxicity, and all of a sudden you're generating 40,000 candidates for a biological weapon. Reality is most of them are not stable and probably are really hard to manufacture, going back to some of the comments earlier. But you can, go after properties both benign and malicious in this category. And then finally, one of the key elements of testing, if you will, the manufacture of a molecule is a process called synthesis, or in the case of if you want to figure out how to make the thing that you've just come up with, the idea of retrosynthesis as part of this. So this is literally the path of a reaction, a state change within a set of molecules that combines the molecules to create a new one, or the reverse engineering of that process overall. We also happen to connect that to a robotic lab, so in certain configurations and targets, you're able to essentially prototype the molecule once you've defined and validated it from that flow. So the whole idea here is all these things are driving acceleration through what is typically a bench-driven process from a chemistry perspective. So chemistry, as I mentioned, is the study of properties and the behavior of matter. In many cases, our objective in application of technologies to this area is not to change any sort of viewpoint around that, but to open up new opportunities to that perspective and how it works. We really feel like this is a worthwhile activity, and in many of these cases, we're driving in that direction. So just to give you a little bit of a read of what I've just mentioned, we have the idea of a set of reaction conditions, which is the input set, if you will, that generates a molecular structure that has certain properties that you're interested in. And within that set, you also have a set of target properties that you want to express through that molecular structure. So there's a constant feedback loop in terms of evaluation of both directions of this category. So synthesis, retrosynthesis, and then reaction prediction and property prediction are really the key to this game overall in terms of what that looks like. Now, that sounds like an open space to interpret how this works, but the reality is that chemistry, like almost every other science, has its own biases built into it in many cases. So we are really comfortable with the idea of, for lack of a better term, flat molecules. Because we've had the language to describe them, they're easy to configure, and certain types of cross-coupling is very easy to do. So most of the drugs we make are flat. Not because there aren't many non-flat drugs, it's just that's the area that we've been scoped in terms of our evaluation overall. Which means that there's a whole universe of non-flat things that could be really helpful, but we have to move past the prior art because the prior art has been essentially constraining the search space that we've been using to define what we're targeting. In this case. And this is just another example of where novel AI applications that are unconstrained in the sense that they don't care about dimensionality. In fact, they thrive in it. You've got a great opportunity to do some new things that otherwise you wouldn't be able to. As part of that. So we're really excited to push in that direction. But there are some interesting barriers as well. Part of that bias in terms of understanding and interpreting the idea of representing what those molecules look like is also constrained by the data and language that we use, right? So we use a bunch of text-based formats like smiles, selfies, Inchy, a few other categories, which are very common ways to describe a molecule. But in many of these cases, you can describe a molecule using many different versions of smiles or selfies itself. You could describe different molecules in a similar fashion with this, and most of the structures or natures of bonds that make up molecular structure are poorly described in, again, a two-dimensional interpretation, which is essentially where text comes into play here as part of it. There's wonderful things like radial bonds in hexagonal structures that distribute charge state quantum mechanically across all of the connected molecules that you can't really write really well in a sequence of letters, unfortunately. So the real question, I think, moving forward for us is how do we take what we know about the world and how it works both in a pure sense, probabilistically, quantum mechanically, and express it in a way that drives those characters. Not too different than how do we express a specific form of logic or an operation in code, how do we describe the relationship of data in this category, we need to start evaluating and building out some better understanding of what that looks like. Which I think, incidentally, is what we're really struggling with overall right now in this age of new AI. We've been working so hard for the last 40 or 50 years on encoding human consumable data in a machine-optimized format, e.g. putting stuff into a database, for example. And now it's become possible for us to take encoded machine consumable data and store it in a human-optimized format, meaning put it into text. I posit that the folks that take this kind of challenge for right now and skip the step in the middle, which is an encoded representation, will be the people who win this little battle, right? We have a great space in terms of a capacity to describe how things work, and it is one of the most commonly used, essentially descriptive tools we have. It's the language I'm speaking right now. It's English, it's German, it's French, it's Spanish. It's a lot of the fundamental formalized human languages or modern languages that you can use to describe things. That is the embedding space. That is the area by which we should be able to describe and effectively drive interaction and change as we continue to grow. We're going to need intermediate representations like programming languages in the short term to prove that we know what we're doing, but I think the ultimate goal is to push past that step to the point where what we describe is what we create, ultimately. So, how does this relate to the OpenAD framework? The OpenAD framework came to us because just like everything else, there's never one way to do something. We have folks who are bench chemists, meaning Erlenmeyer flasks and goggles and gloves. We have folks that are pure computational chemists that only work in a synthetic environment. We have people in between that are trying to balance between these modalities in terms of how things work. So we had a lot of different audiences to think about when we were putting together a framework to help with that acceleration overall. We think that by pulling together a single tool set that has many different faces, we're going to have an opportunity to get people to collaborate and drive things that we often take for granted in this situation, especially in the case of open source software, like repeatability. Repeatability for an experiment, sounds like an odd combination of words to begin with, but it's a really important one ultimately as part of that. So the OpenAD framework gave us a couple of important opportunities to correct for some of those initial lines of thinking and to move more toward a repeatability target in terms of the interpretation, and gave us a great chance to test some of these new technologies in terms of their capacity to assistively and adaptively describe the work that people are doing. So we put together a simple single API that feeds a CLI, an API, and some notebook extended services because scientists love notebooks. I don't, but they do, so we use them. We integrated all the view of those pieces together, and we added tools that took things that were better expressed as visual context out of the 2D realm and into the 3D realm in terms of molecule viewers, runs, LLMs, et cetera. And then we consolidated all the ilities, like security, data access, collaboration, and put that into one single flow so that you don't have to worry about where it is or where you are and what it looks like. And then we made it extensible. So if you come up with a novel form of simulation or a novel form of candidate validation, you can use all these facilities to essentially extend and drive those pieces. And then we added the capacity to record, store, and manage experimental workflows, right? This is really important. What's the best way if you don't have a predictive path through a specific experiment? Record what you did and eliminate the parts later that aren't relevant or you believe aren't relevant to the overall experiment as part of that story. So that looks essentially something like this. We have a notebook-based framework that lets you do that. We have the CLI side of the story, and then we have a strong DSL that we use to express workflow steps in a very clean and organized fashion. Like, I would like to get X from Y, rather than working about another pragma or a structure that you might need in this case. Now, this is the point where I wanted to go to a demo, but I am happily right now working on Dean's machine because mine decided to not connect to the projector, so I'm just going to walk through the demo backup I've got at this point. So a great example of this is this idea of being able to pull out and have what I think of as self-describing or self-documenting set of commands that might be appropriate in this situation. So for each of the frameworks that gets integrated, we essentially use an LLM to vector embed the base documentation into each of the segments that are here. So if you wrote the docs, this system can answer questions straight from the docs in terms of what the function would be. So you can combine a set of functions to do this. So this is coming out of a Llama 2 ChromaDB combination that we've put together that sits alongside the standard software. We really like that idea because you can write something once and make it a usable user functional characteristic. In this case, we're going to play with deep search, and we're going to look at and list some properties that have come from some patents in terms of what those targets look like and how it can work. So that usually constitutes searching for through a set of papers for specific molecules that might be relevant to the topic areas. So in this case, we're going through some archive abstracts, and we're extracting some interesting information about power conversion efficiency and a few other arguments, and we're pulling those out. This type of viewpoint comes back to the user either in the notebook they're executing or through basically a Flask app that we kick up that goes straight into the web browser from the command line, which you can also invoke through the API. And all those tools and capacities are generalized so that if you're a scientist and not a developer, you have a great opportunity to just use what's available to give people immediate access to how those tools work. So say we find a property that we really like, and we think, hey, that's great. Let's evaluate what that looks like from a molecular structure perspective, and let's find some similar molecules. What often happens in chemistry is that the great idea that you have, it's a good chance, especially if you're working in 2D chemistry, someone else has come up with before. And not only have they come up with it, they've patented it and put it into a database at their company, just in case they need it later, because that's how patents work. And puts you in a place where you might have a desired property or desired structure that needs to be expressed differently in order to essentially characterize a molecule that you can own, if you will, as part of that story, which is a whole other problem, in my opinion, in chemistry. We'll leave that one alone. So great way to do that is to do a molecule structure similarity search against this database, get a good look at what that looks like, how it works. This system itself isn't that complex. It's essentially Lucene on top of Elastic, but we've built some very, very specific parsing capacity for use in this domain. A lot of that, to be really honest, is starting to be replaced by some of the core features in LLMs, but we're going to continue to mix that in as we go, as we continue to develop it overall. So once we have a set of candidates that make some sense, and we've got a good view of what that looks like, you can go ahead and pull up a set of molecules, evaluate which ones are immediately interesting to you, how this works. You can kind of play with the representation and targets, and you can do that. So we also built in not just the documentation view of how that works, but a capacity to combine commands through a little bit more of a complex embedding scenario here. So we have this thing we call the how-to assistant. So you can ask OpenAD how to do something specific, like identify a property and then evaluate it in terms of potential synthesis path. So you can combine the tools that are in there so you can quickly establish that. And if that one specific command doesn't work, no problem. Remember, you're recording this. So you're going to be able to essentially extract the bad value or augment it later if you need to. But more importantly, you have a record of what you did so you don't have to remember in this case. So this is a great example of just a direct output that gives you a clear, visible understanding of what the tool and framework is. And this is nothing more than some chunking and vector embedding. This is a LangChain app that we added to this as well. So once we have a good sense of what that looks like and how it works, we can grab that molecule. Most chemists want to see a molecule because the structure is something that they remember, like the texture of your favorite keyboard. in many cases. It's a very comfortable and familiar area, and visual verification is pretty important, so we definitely show people what that looks like. We also happen to store it as a data frame behind the scenes, so if you want to play with it right away in terms of manipulation, it's pretty much directly available. And once you've got that going, you can essentially drive a prediction of the retrosynthesis process that's available from that perspective. So we take that molecule in, we show it to you in 3D, because as I mentioned before, it's probably pretty important, and we evaluate the output and push this in. So right now, we do a couple things. One, we use a generic property prediction to chemical output scenario, which is essentially nothing more than a next token problem. But we're starting to do what we call state change interaction graphs, which are starting to describe better ways to evaluate things using something called method-based chemistry to help do this. And we're doing that combined with a framework called Ray, which you might have heard of several times today already, to be able to dynamically scale the cluster that executes it based on the scale of the molecule you're processing as part of that story. So it really helps a ton to be able to scale those functions. We often use also another interesting tool that you might have heard about if you were downstairs called Dapper to handle all of the common security, secrets, access management, and other structures as part of that to simplify the service deployment in those cases. We think that kind of combination of things that have a lot of scale from zero based properties really gives you a great opportunity to do some solid runs in terms of those characteristics. So great, we'd like that molecule. We put it through the RxN retrosynthesis tool, or sorry, synthesis in this case, and we come back with, and unsurprisingly, there are many different ways to perform synthesis for a specific molecule that you need. Now, why do we need so many of these? Some of these are practical, right? Some of these might require vacuum to be performed. We've got to get a good sense of what the constraints or targets in that case looks like and how it could work. This is where you're moving more out of the scientific discovery phase and evaluating the overall cost or value engineering necessary to produce the molecule itself. So I imagine I would pick 2 or 3 of these. They make sense to me, and I might say, hey, I'm going to send this synthesis path to RoboRxN, or if you have a lot of money and you're working in an industrial lab, a ChemSpeed or something like that, which is a real industrial grade lab, and perform some prototyping activity. Once you get that back, you have a good sense of what it does, what the constraints are, where it is, and what's it going to cost to build, and can you scale it? Which sounds to me like acceleration overall, and that's really where we're headed in this case. Now, I didn't say a lot about simulation, because right now, in many of these cases, the advent of generative candidate identification that I mentioned earlier, GT4SD, has done really interesting things to the profile of compute that we're applying to these problems. Before, most chemists or medicinal chemists would evaluate a couple key molecules that they thought were sure bets, and they would go in and do things like docking simulations or in situ molecular dynamics, which are really expensive high-performance computing operations. But the way things are moving right now, you can generate 40,000 candidates and evaluate their synthesis profile and quickly determine if any of them are practical before you spend any of the money on high-grade simulation. And high-grade simulation at the top end is really where things like quantum computing come into play as well, right? So you may do something simple like a single operator validation of the polarity of a molecule with a quantum system, or you might look for small molecule observables, thermodynamic observables, which are really high-end problems to deal with, just to be super clear in this case. But again, these are all things you can plug into this OpenAD framework and quickly and rapidly establish their relevance to an overall molecular discovery workflow as part of this story. So that's really where we want to go to. Oh, by the way, part of the synthesis path output is the recipe. So stir this many times, this much in this situation as part of that, because, hey, humans make this stuff too. We're not always We don't always have a robot around to do it for us, as sort of from that perspective. And then, we have forward prediction for batch and a variety of other scenarios. And all these tools, by the way, also work straight out of a CLI as well. Many HPC technology aficionados, if you will, use things like Balsam and other shell-based workflow tools, and we need to stay compatible with this. So there's nothing wrong with embedding an OpenAD call directly into your existing HPC workflow as part of that story. In fact, I think that's an ideal state. And the same fully integrated help works in the command line view, as well as the direct API use as part of that story too, as well as all the molecule viewers and inlines. You can kick those off straight from the command line as well as part of that story. So the whole idea here is we want to take care of all the software-related repeatability and accessibility concerns so you can get down to work and really drive the scientific output that you need using the fastest tools that you have available at any given time as part of that, and push in those directions. So I wanted to share this with you because I think it's a really great intersection of open science and some of the key principles of AI and applications within this time frame, and kind of embodies that spirit of exchange of information between open source software and open source science as part of that story. So, any questions, folks? I think I'm on time, yeah? Right.
Yeah, let's do, you mentioned in passing that quantum computing is starting to be applied here. Maybe you could talk a little bit more about what people are doing with them in this context.
Sure. So quantum computing is interesting, right? Because it's a probabilistic evaluation of certain states being driven in this category. Most of those states are described in something called a Hamiltonian, which is a perfect definition of an energy state. And that's how, believe it or not, electrical qubits work. So there's a very natural correlation between articulating the energy state of a molecule and articulating the energy state of a combined, or a set of entangled qubits. So a lot of the early applications for quantum computing has been chemistry related as a result. But the problem with that is that we only have so many qubits entangled right now. So, and if you get more than like 10 or 20 or 30 together, you end up in this wonderful universe of distributed quantum computing, where you actually have to register the superimposed qubit values across a classical computer and then perform stochastic or essentially repetitive options to get an opinion as to what the state is. So there's lots of extra compute that goes into a hybrid quantum classical calculation of an energy state as part of that story. Now, in a perfect world, we take all that mumbo jumbo I just said, we put it behind an API, and we have the system do it for you, but that's kind of where we're headed currently.
I think that's our time, but the Q&A table number 2 outside. Thank you very much.
Thanks.